everyone. Thanks for coming for the next Warsaw Quantum Computing Group meeting. Today the lecture will be given by Oskar Słowik, titled Introduction to Quantum Walks on Graphs. And this event is supported by our main sponsor, Daftcode, and also by Codecool. So this is the first meeting here in Codecool, and Adam from Codecool would like to tell you a bit about Codecool. So Adam, can say a few words?
Yeah. Hi everybody, my name is Adam. I'm a mentor here at Codecool, and it is my privilege as the host of today's event, this one, to tell you a bit about our school. Well, we are a programming school that started in Warsaw 2 years ago, but the school itself is from Budapest, from Hungary, well actually from Miskolc in Hungary, where they started over 5 years ago. So we already got some experience into how we work with our students. I'm going to tell you very swiftly about our school, about who we are, about what we teach here, and about who we teach. So, first of all, people ask us who is a typical student here, who can apply. Well, there is no straight answer. There is no typical Codecool student, because we got people from every background, from different age groups, starting from 18-year-olds who just finished their schools, through students who, well, chose the wrong studies and decided they want to become programmers, all the way to people who have already finished their studies, worked for many years in their respective fields, and also decided to change their lives. So the only common denominator with our students is that they want to change, they want to learn, they want to grow and become programmers. So this is a typical Codecooler. Our school is divided, well, the course takes an entire year. Because it's a very intensive course, we don't want to teach a single technology, we want to teach how to program. So our course is divided into 4 parts. In the first one, Prog Basics, we teach how to work with, well, how to start programming. We teach how to work with variables, how to use if statements, how to use loops, how to develop a proper architecture, how to develop clean code, how to develop your first algorithms, what to think about when you do it. Afterwards, after about 3 months, students move to the second room where we teach web and databases. So we add responsive and beautiful UIs to the basics of programming. We add JavaScript for the pages to be responsive. We set up servers with Flask so that our students can get a wholesome experience of their websites. The third module is the object-oriented programming module, where, based on C# and Java, well, we teach the principles of object-oriented programming. We give more insights into how we should plan our applications, how to develop them, how to develop a proper architecture. After about 9 months of coding and working, our students go into the advanced module, where they develop their own projects based on the technology they want, and also the technology that is most sought out in the professional community. Because our goal is also not only to teach the students, but also to help them find a job, find a good position as developers. During the whole year, we also teach our students how to work with the most common tools used with development. For example, version control tools, IDEs, etc., etc. Apart from the hard skills, just learning to code and learning a concrete language, we also teach the more fundamental aspects of programming, which are not connected directly to a single language, but are more universal. Which data structures to use in which algorithms, how to optimize our work, how not to put so much boilerplate code, how to keep our code clean. hard skills are not the only important thing that we teach, because apart from that, we also teach the methodologies of working. We start with pair programming, and morning dojos that prepare everybody to the tasks that they are going to be working on. We try to implement Scrum and Agile development as early as possible, so as to simulate a real-life working environment. We teach people about waterfall and why it's not advisable to use it. Our students learn other methodologies, for example, test-driven development and how to use the unified modeling language to communicate how your application is going to be structured. But there are also soft skills, which are very important, because as all you probably know, the stereotype of one lone programmer sitting alone in a basement and coding his own app is, well, it's no more. Now, every big company needs programming teams, and they need to communicate well. They need to share their knowledge between each other. They need to be able to work with their time. This is a very important part of what we teach here at Codecool. So, I blasted through this presentation as quick as I could to give you as much time with our quantum group and with the lecture upcoming. But the most important thing I came here to tell you is that we're looking for mentors. We're looking for people who are driven to help others learn, to enhance their futures, to change their lives. We need people who are strong technically, but can also pass their knowledge, and who want to pass their knowledge. Well, I have today a question: what is the difference between us and a boot camp? The main difference is that we do not teach a programming language. We don't want you to learn a single language and be able to, well, solve some schematics. We want to teach you to program, to know how to use any tools at your disposal, how to find your own answers, and how to pose your questions so that you can find those answers. So if you are a person who would like to become a mentor, or you know somebody, please give us a call. You can find us at codecool.pl. Yes.
Are you going to teach programming quantum computers?
Well, that would be great, but I am afraid that 1 year to master all the fundamentals of programming would not be enough to add also quantum computing. That might be a bit of a stretch. But who knows? Maybe we can branch out and start with more advanced courses.
All right.
Right now we are working on with people who haven't coded before, and after a year, our goal is to change them into, well, something between junior and mid-level developers.
So just one thing to add, that our course is like a mini environment. We try to simulate the normal work environment. Our students have projects, team assignments. They work on their own during the self-assessment, self-improvement weeks. But, so we asked about quantum computing. Actually, we want to introduce them into quantum computing, because I myself took part in this course. It was in June. Was it in June?
Oh, you mean the workshop?
Yeah, the workshop.
It was in May.
Yeah, exactly. So we want to actually show them, introduce them in one of our Flash Talk days, where we introduce them in some kind of quick ideas, and one of them will be definitely quantum computing, and perhaps we will have a spin-off of a mini workshop in quantum computing. So yes, we will.
Sounds good. Thanks, thanks Szymon, and thanks Adam. Yes, so the lecture will start soon, but I know that Professor Piotr Gawron, one of our past speakers, would also like to.
Hi, my name is Piotr Gawron. I'm Professor of Computer Science. I'm looking for researchers at early stage of development, so master students, PhD students, and postdocs here in Warsaw in quantum machine learning and signal processing in #, a new research agenda established here in Warsaw. So If you're looking for a job in academia, academic job, please talk to me later during the pizza time or any moment you wish. And if you are in a hurry and you have no time to after the talk,
Nie, tylko Mozilla.
Thanks, Piotr.
So hello everyone, I'm Oskar Słowik and I'm a fifth year student at the Faculty of Physics of the University of Warsaw and Faculty of Mathematics, Informatics and Mechanics. And I'm also involved in some research at the Center for Theoretical Physics, where I work at Adam Sawicki's group. And our domain is mathematical physics, also theory of quantum entanglement, and recently quantum computing. And today's talk will be about quantum walks. I'm not by any means an expert in this field, but I gained some experience because I was experimenting with IBM Quantum Experience 2 years ago, and I used it to run some simulations which were implementing discrete quantum walks on some graphs with some specified topology. So today I would like to give you a short introduction to this topic and get you acquainted with the basic concepts. So outline is the following. Of course, an introduction, then I will describe what are classical random walks. I will maybe recall probably, because I think majority of people here have computer science backgrounds, so almost certainly they met classical random walks somewhere, for example in some algorithms. Then I will start from continuous quantum walks, but I won't concentrate on them because our implementations will be interested in implementing discrete random walks. So first I will describe the simplest example, a discrete random walk on the line. And then I will try to say a few things about efficient circuit implementations of discrete quantum walks. So how can you actually implement them and program something and run it and look how such walks behave. And then I will show you some not very interesting results of my simulations and probably summarize. So firstly, I would like to give some applications just for motivation of classical random walks. So they can be used in financial economics for modeling share prices and other factors like this, in biological sciences, in genetics, in physics, in various other areas of science, from brain research to psychology, also in gambling. But we will be mainly interested in applications in computer science. So in computer science, they are usually used as sub-procedures of algorithms, so-called random walk-based algorithms. So these algorithms may be, for example, used for complex network analysis, estimation of size, so number of nodes, links, triangles in some very complicated network. For example, maybe, I don't know, Twitter or Facebook or another very complicated graph of connections with many nodes and a lot of data to analyze. Also detection of central nodes, for example, top k largest degree, a list of top k largest degree nodes, and network clustering. Another thing I found is application in image segmentation. So I think this is something maybe Professor Gavron would be interested. I mean, on the quantum version especially.
I did the quantum version of that.
Yes. Okay, so I also found an application in art. I wanted to show you, sorry. Okay, so this is a sculpture in London. It's called Quantum Cloud. And this pattern was generated using classical random walk. And inside there is, I think, something which resembles the author of this sculpture. And from the surface of this of this bulk, random walk started, classical random walk, and this is the pattern it generated in space. Okay, so maybe just recall what the classical random walk is. So this is a stochastic process, and we need to have a space. So it can be anything reasonable like line, vector space, Lie group, manifold, or in particular we will be interested in graphs. We need to define transitions. So the set of rules how these states will transform over time, or and of course we can have discrete or continuous time. So in case of discrete time, we can think of number of steps, discrete transitions, and in case of continuous time, we have obviously like some continuous change of probabilities. So an example of such a thing is our Markov chains and Markov processes. So they are processes without memory, which means that the set of transitions which are at the moment depend only on the what happened just one step before. I mean, an update depends only on the actual state. So there is no memory of the history of the process. And here we can identify two like basic parameters. Maybe I didn't give any mathematical definition here because I think it is like I found various definitions and I just wanted to give you just an intuition what these things are. So a heating time. So when we have two vertices chosen, one of them will be target vertex, another will be source vertex. We can look at the expected time needed to go from the source to the target vertex, and this will be the heating time between those two vertices. And whereas mixing time will be time needed for probability to spread all over over all vertices. So in case where our process has the stationary measure, which is sometimes the case, then it might mean that just our probability distribution becomes very close to the stationary measure. So this is the time needed for our distribution to be very close to the stationary measure of our process. So the simplest example would be time homogeneous Markov chain, where just these probabilities that do not depend on time. So we have just some fixed matrix of probabilities of transitions between states. So here we have two states and a matrix of probabilities. This is the stochastic matrix, which in this case means that sum of the rows add up to 1, which means that the probability is conserved during the process. And okay, so here the notation is that I multiply, I take a vector at the left because it is a row vector. So this is just a convention usually used. And so my update rule would be that when I start from some initial probabilities of being in A and B, then my probability at next step is just this matrix multiplied with the vector of probabilities at the previous step. Okay, so I can easily calculate my probabilities just by taking powers of this matrix. And the stationary measure is just a measure which may or may not exist, it depends on the process, such that it's invariant. So this is a choice of probabilities which remain invariant under this matrix, which means basically that if I start from this set, then nothing will happen. But there is a very basic theorem which says that, for example, there are various theories which say whether our process will or won't have the stationary measure, and if or whether it converges to this stationary measure. So, for example, for each aperiodic and irreducible finite Markov chain, so this means that the set of states is finite, there exists a unique stationary measure, which is just the inverse of the expected number of steps needed to go from J back to J. Okay, so this is very intuitive. And aperiodic and irreducible means basically that irreducibility means that I can basically reach from any state I can reach any other state, and aperiodicity means that the period is 1, which means that if I take any state and I will look at the number of steps needed to go back to this state, and I will take all these numbers, then I can look at the highest common divisor. And if this divisor is 1, then there is no period, and such a process is aperiodic. Okay, so this is just an example of theorem we can use. And in this case, we know that this measure is unique, and our processes converge to this. Of course, there are many processes which do not have such a measure. For example, the simplest walk on a real line does not have a stationary measure. So, because it does not have a finite number of states, right? So I cannot apply this. I mean, this is not implied by this, but I cannot apply this theorem. Okay, so let me introduce the simplest example of random walk. So I have a graph, a stochastic matrix, and I can just say that define the stochastic matrix like this, that if I am at some vertex, then I will, if equal probability, so here is a degree of this vertex, go to any direction. And this will give me a stochastic matrix, and this is like the simplest possible choice. And now I can look at continuous random walk. So I have some graph with some specified. I can calculate from the structure of this graph. I can calculate adjacency matrix, and which is defined here, and Laplacian. And I can just construct diffusion equation for the probabilities of my of being at given node j. Okay, and connect it with the Laplacian with some coupling constant. And I can solve this for probabilities, and I will get just this simple solution where here I have the Laplacian for the graph. So this gives me the continuous walk on a random walk on a graph. And how can I, let's say, introduce something quantum? Well, I have this diffusion equation, and Laplacian is Hermitian, okay, because it's real and symmetric. So I can treat it as okay. Now I can use it to construct Hamiltonian for my quantum dynamics of states. Okay, so I have some Hilbert space which is all the positions, and it's finite, and my quantum states lie in this Hilbert space, and I connect probabilities, these classical probabilities, with amplitudes. And what I see that this diffusion equation is very simple, similar to Schrödinger equation, and I can just take IL as my Hamiltonian, and I will get such a solution. And of course, instead of L, I can take any Hermitian matrix which respects the structure of G. For example, instead of L, I can take an adjacency matrix. Okay, so now I can think how this classical and quantum continuous walks differ in terms of this mixing and heating types I tried to introduce. So in general, quantum walks can take advantage of faster heating or faster mixing, and there are now examples of graphs where this heating time for quantum walk is exponentially smaller than from classical random walk, so it's exponentially better in this sense. But difference in mixing times, so can be in general case only quadratic and no more than this. And of course, one should remember that faster heating does not immediately imply any algorithmic speedup. So here there is an example we have three graphs. We can generalize them to any n of vertices. Okay. So here I will have hypercube, and here I will have just more vertices. I mean bigger depth. And I can look. Okay, so I have the following problem. I have the labels. So this is the problem with the oracle. I'm starting from A, and I need to find the exit. And I have the oracle, which will give me, and here I have labels of these vertices. And oracle will give me, at any, if I give my actual string or name label of vertex, then it will give me all neighbors, all strings of neighbors, and I need to deduce what is the label of output. Okay, so in this case, continuous classical random walk requires exponentially more queries to finish this task. So to reach this exit starting from edges, but the difference is that there exists some classical algorithms which do the same job equally good as this quantum walk, whereas in the third case there is none. And I think this was one of the first examples of showing that this continuous quantum random walks can do something exponentially better than any classical algorithm. So it is proof that there is no such classical algorithm which will do it as well as continuous random walk. So this is in fact a result of Childs. So here is this setting I described. We have these vertices which are random bit strings. We know the entrance. We have the black box, and we want to find the name of exit. And any classical, so D here is the depth of this tree. So I have like two binary trees, regular, and they are interconnected here. And if I will connect them in the regular way, like this, then I have a classical algorithm which do it the same. This solves this equally good as this quantum continuous walk. Whereas if I take here random interconnections according to some cycle, then there is none. We don't have any classical algorithm. It cannot exist, which will do it equally good. So it is. So we have exponential speedup. But this is very, very specific problem, very specific topology, and very yes. So okay. But this is some motivation why this quantum walks can do something beneficial for us. Okay, so let me recall that the basic properties of discrete random walk on lines. So I have a line. It's discrete, so I take z, and I start at some position 0. Okay. So my state will be not only the position n, location, but I will also introduce direction. Okay, so let's say that 0 will be right direction and 1 will be left direction. So I denoted directions by these arrows. Okay, and I have this update rule that I will change my direction with equal probability, and then, so this is the first step. Either I will change my arrow or I won't. And then I need to move according to the actual current direction. Okay, so this is exactly what happens. And this is the discrete random walk on the line. And of course, expectation value is 0 of my position, and variance changes as a square root of number of steps or time. So, and I get such a probability distribution. So here is number of steps, and here is the probability. So it looks, for very big types, it looks Gaussian. So how can I introduce something analogical? I will have a line, so my positions are are just points on Z, and I have one Hilbert space for positions. It is infinite dimensional, okay, and I will expand it by some auxiliary space, on which the coin operator will act. So previously, this coin was just this change of direction, and then there was the second part where I updated my position according to the direction. So here I'm splitting by unitary evolution using two operators. First will be the coin, which will be like this, that I will just, this is just this Hadamard gate, okay? This is the Hadamard coin. So this is just the action of the Hadamard on such a state. And then I will use shift operators. So basically, I will be just shifting according to the direction. And what will I get? I will get such distribution. So here is this distribution depends on the initial condition. So position is at 0 in both cases, but I can also have the freedom of the choice of my left or right, and I can also take any superposition of left and rights. And if I take such a superposition, which is much more symmetrical choice than 0, then I will get the symmetric distribution. Otherwise, it will be biased because I chose one of the directions. And what is interesting is that the variance now changes linearly with number of steps, not as a square root. So this shows that somehow this walk penetrates the structure of line quadratically faster, at least in terms of the variance and another thing is that it is totally different, okay? Here I have the very strong peaks, kind of fronts which propagate, and here at the beginning where I always have maximum, in the classical case, I do not have much probability of measuring my quantum Walker, okay? Because in the end, because I didn't say that, I need to perform a measurement, and then my Walker will appear somewhere according to the amplitudes of the current state. So how can we understand this? So this is just a result of interference, of quantum interference. So here, notice that if I go left, then I, with equal probability, remain going left, and with equal probability, I will start going right, but I won't change the signs here. Whereas when I'm going right at the moment, then with equal probability, I will turn left and turn right, but here I change the phase factor. So there might be some interference. So let's look. Here, so my coin space is two-dimensional because I have two directions, okay, and I can take any superposition of this direction. And so I will show how the evolution looks for everything going right here, and how evolution goes for everything going left here. So this corresponds to the basis vector of coin space 0, and this corresponds to 1. Or other way around, because I maybe made a mistake, but let's look. So I apply coin. So yes, it's split. They all point up, this amplitude. So here I imagine that I have some normalized amplitude, okay, to 1, a state. And I will here denote these bars will correspond to the probabilities of which correspond to the amplitudes, but I will also denote the side of a phase, so going up or going down. So here I apply coin, so I split to going right and going left. Then I need to update. So as I said, one step is applying coin and then shift. Okay, so after one step of my walk, I will get this. So I applied shift, so this went left and this went right. Okay, so this is left and this is right. Then I apply cone once again, so this splits, this goes left, so they will all both point up, and this goes right, this goes left, so this will change the sign. Then they shift this on left, this on right, then I apply this once again and shift it, and then I will measure. And here I denoted amplitudes, which are proportional to the length of these bars. So finally, after measured, we will get just a number, which is the position. So if you do it many times, then we will be just probing this probability distribution, which is de facto, this is deterministic, truly deterministic. This is just a unitary evolution. So there's nothing probabilistic here. The only probabilistic act is the act of measurement. Okay. So how we can try to implement such discrete walks on, let's say, arbitrary graphs? But maybe not arbitrary, but on graphs. So something slightly more complicated than line. So here I just recall some basic building blocks. So we can use classical quantum L registers. We have, of course, single qubit and 2-qubit gates at our disposal. Let's say we have CNOT and we have swap, and of course we will have a measurement. So here I just show you the Hadamard gate, which is exactly the coin I applied for the line here. Okay, because this coin acts non-trivially only on the coin subspace, whereas shift can act non-trivially on both spaces a priori, but here it acts only on the position space. Okay, are there any questions at the moment? I mean, is anything not clear? Okay, so yeah, so I will use swap and C dots. So C dot is just the controlled dot. So if so this is the so here I have the Gaussian, and this is the this is target, and this is a control bit. So if qubit, so if it's 0, then nothing happens, and if it's 1, then I will have a negation here. I have the Gaussian block. Whereas here I have swap, so it will just remain 0, 0 at 1, 1 invariant, and 1, 0 will go to 0, 1, and 0, 1 to 1, 0. Okay. So this is what I will use. And now let's discuss the general setting. How can I try to define such coin walks? Because this is just one of the approaches. Another approach is Szegedy walks, which stems from the quantization of classical Markov chains, but I won't discuss it. So for such coin walks, and for some I-directed graph with number of vertices and a number of edges k, I will consider extended space of states. Okay, so this will be my vertices, and here I will have. So here these are called nodes, and here I have what? Well, subnodes. Okay, so this is the nomenclature. So subnodes will at a given node I will have di subnodes, where di is the valency of or degree of the vertex. So if I have vertex of degree, for example, if I have a graph like this, then my Hilbert space of positions are this 1, 2, 3, 4, 5, 6, 7 points, which span my Hilbert space for positions. And here I need to have coin space, which I will have 4 subnodes. Okay, so it will need to be 4-dimensional for this node. So in general, I will need to look at the highest valency or something to be able to do it. So okay, now So by Hilbert space, it will be extended by this auxiliary coin space, and my update rule is just this coin and shift. So this is a shift, so shift will just do something, provided the only constraint in the most general setting. This is very vague, okay? So this is just general rules. It gives you a lot of freedom how to define actually these operators. So I can do anything. It can act non-trivially on this and on this, but to which I transform the node needs to be connected with the previous node. So this is just reasonable assumption. So this C will be just bunch of DI times DI unitary operators, which will just independently mix all these subnodes for every node. Okay. So I can think of it as a block diagonal unitary matrix. Okay. So I can easily see that if G is without loops and multi-edges, then S is just 2k times 2k permutation matrix, and C is 2k by 2k block diagonal unitary. And since I have a bound on number of edges by the number of vertices, then I can classically simulate it in polynomial time in a polynomial poly n. So n is number of vertices. So if I even want to think about the possibility of exponential speedup, then my quantum version needs to scale logarithmically with the number of vertices. So when can it happen? When there is, for example, if my graph has high symmetry, but here symmetry does not mean geometrical symmetry, but the some structure which enable me to use at most log n parameters to describe how my graph is complicated. For example, to describe my graph, in fact. For example, if I have sparse graphs with so-called efficiently commutable labels, I won't define this. This is just some specific constraint. Then this should be satisfied. And also, if I have such a graph, then also it means that I cannot have more than O of log n completely random edges. Because, okay, if I have two random edges, then I cannot compress this information about graph to log n parameters. This is just hand waving, but these are just examples of what should we look for. Okay, this is just for you to know that there is another approach, and in fact there is a procedure of quantization of any classical Markov chain given by Szegedy, called Szegedy quantum walks. So I can do the following. I can use my random walk to formulate a generic search algorithm, like in the classical case where these walks are often some procedures in some search algorithms or other algorithms. Then I can quantize it using this procedure. And from some theorem given by Szegedy, I will get generic quadratic speedup. So maybe quadratic is not exponential, but it's generic, so it's like I just need to quantize classical algorithm. So it can give me some speedup. Probably it's problems such as element distinctness, search on grids, or checking whether there exists a max state in my search. Also, I found a nice paper by Locke and Wag where they give a quantum page rank. So everyone knows probably Google PageRank. This uses some ideas in random walks. So they gave a quantum version which is uses this Szegedy formalism. So you can check it if you are interested about the performance and things like that. I won't tell you. Okay, so let's construct something. So let's consider a cycle. Cycles are easy. This is just okay. We understood. Let's say walk for a line. So this is just a line with glued. So we know what happens provided that our probabilities won't start to clash. Okay, because after so for small number of steps, this will be just line. The same thing as for line, but after some amount of steps, they can overlap because they will travel both semicircles, yes? And so then it will be different because the interference is possible. But in fact, it is nice, interesting, because it depends on the parity of number of these guys. Because you see that at every step, only even or even odd vertices have non-zero probabilities. So if this, when I will start somewhere and I will have those two fronts, they can either match, so they will just hit one to another and they can interfere. Either they can go through one through another, because they will be like, you know, translated by one. Okay, it depends just on the parity of the number of vertices here. Okay, so here I have 16 vertices, so I need 4 qubits for the node space. This will be just describe all these positions, and I can enumerate them just 0, 0, 0, 0, 0, 1 in ascending order, such that going left or right will be just the increment on the incrementation of decrementation of some binary number. Okay, and I can so this will be by shift. Okay, going left or right, and for the subnodes, I have just 2 directions. So I will have 1 qubit in the subnode subspace, and I will apply Hadamard coin as previously. And then if I go left, then I go left. If I go right, then I go right, just as I showed you previously for the line. This I can increment easily using controlled nodes. So provided that I can effectively implement these guys, I can try to do something. Another simple example of a graph where you have an efficient realization is the click. So here I have 16 vertices, yes, and so I need 4 qubits, and also I have 16 possible, let's say, directions, because I can go from every node to another, and I also have these small loops here. Okay, you can see. So in fact, there are 16 of them. This is just to have a nice implementation. Okay, because then what I can do, I can just mix all of them using Hadamard. So and then perform swap. So what will happen if I am somewhere and I pointing, for example, to this vertex, then after performing shift, I will go to this vertex I was pointing to, and my direction will change to the direction I came from. This is just such a thing. And for example, it does not need to be click. It can be, for example, click with every second edge deleted in a regular way. And then I will just see erase one subnode, and I won't do anything on one qubit here. So, and I also can do it for glued trees, provided that I have the, for example, here I have efficient quantum circuit implementation of quantum walk for a glued tree with regular interconnections. Okay, so this is something you can construct. And here you have something I didn't describe. This is so-called Grover coin, which is very important, because you can choose many coins. I already showed you that this formalist is very vague. You have a lot of freedom to choose your operators, provided that they are reasonable. So you can also choose different coins. And so, for example, there is a Grover coin. I already showed you. There is Hadamard coin. There is a Grover coin and, let's say, a Fourier one. And it matters which coin we will use. But so, for example, the Grover coin is nice because it is the only matrix, unitary matrix, real, which is invariant under permutations. So it will be invariant with respect to the relay link. Okay. So that's nice, a nice feature. And And I can, of course, easily implement Hadamard if my number of just by plugging Hadamard on every qubit when my number of vertices is power of 2. As for Grover coil, I can make it work for arbitrary number of I can introduce generalized Grover coil, which will be possible to construct for arbitrary valency of vertices. So maybe I'll show an example where I construct such a coil. So I wanted to implement a program which will generate QRSM code implementing quantum walk on such a lollipop graph, because this is something which just is which consists of elements we already know they have efficient implementation. So my question was just as a simple exercise: how would I construct such a, and also in order to trade QSkit, how would I construct such in an efficient way such a walk? So I can of course divide my by lollipop. So lollipop is just a click with a line. Here I have lollipop with small loops, because then the implementation will be easier. So I can address it in a reasonable way, and then divide it into sections for which I know they have different dynamics. So for example, if I will go here, I will need to go back because there's no loop. Here I have a line. So line is just a circle, part of a circle. So I have increment, decrement things. I can do it. This is just part of a click, and this guy is problematic because it has degree 5. So here I would use generalized Grover coil. And this solution has one parameter, which for simplicity I assume that I will have one parameter of the size. So this size is number of vertices 2 to the power n plus 1, which means that I have just 2 to the power of n things in click and 2 to the power of n things on the line. So it's like a specific choice of this ratios between vertices in click and on line. And I wanted to look at what will happen with my code when I will increase n, how it will scale. So as a measure of complexity, I just took, for simplicity, number of QRSM lines of code my program will output. OK, so this is just a thing you can easily construct. So just do it in the following way. Firstly, identify. So this is for this, in fact, for this n. This is the circuit, but I did it that my circuit builds up for arbitrary n. So this is just to show the general how it works in general. So I will have a combinatorial block which will just look at which sector I am, and because I have very not dump addressing, I can do it pretty effectively. Okay. For example, if I have 0, then I know I'm somewhere here, so I can just very quickly find out from the address where I am and which dynamics I should use. I can effectively implement. So I will just encode this information in some alcilas and then do conditional dynamics separately, and then conditional shift operator. So this will be coined when I'm in a click, and this will be this will be in the G5 will be for this node, generalized Grover coil, and this will be to address section 4. And then I need to uncompute ancilas, because this is just one step. This is one application of one step of a walk. So my circuit will grow linearly with number of steps. So I will look at, of course, just the number of lines for one step. Yeah. Okay, so some technicalities I'm not gonna tell you because they are not very interesting, is that you need to efficiently implement generalized C-dots, increments and decrements, and I can tell you that you can do it just using some, well, I just found a solution on the blog of a guy who apparently found out how to do it effectively, so I used his algorithm as a subroutine in my program, and I have this part solved. The only thing was to implement generalized Grover coin. So the point is that I have here valency 5, okay? So, but this operator will operate on 3 qubits, so it needs to remain those 3 subnodes need to remain invariant, okay? So I don't want something like this, but I will have 8 by 8 matrix, and here I want to have this block and here identity. So you can easily do it by state preparation, I can say, and so this is very easy. So in fact, you can implement everything on Qiskit, run it, and now I will maybe show you how it scales. So this is a result for number of quantum assembler lines versus number of qubits. So here I have number of qubits, and here is the number of QASM lines for one step of the simulation. So here, for example, we have 20,000 and things like that. So this is like a lot, I would say. Of course, it looks like it is linear, which means that it's logarithmic in the size of a graph. Okay, and here are some probability amplitudes. They are not very interesting because I was doing this simulation 2 years ago when Qiskit was much more primitive, and I have no ability to look directly at the states. I was only be able to do measurements, and I need to do it many times on my local unitary simulator, and my computer was not able to generate more data. So sorry. Now it's of course much more easier because I do not need to do 10,000 runs or things like that and average it and do histograms. I can actually look at the evolution of a state, which is million times simpler. So probably I will do it once again and will generate more data because. So this is a result for a cycle with n equals 6. So it is 2 to the power of 6 nodes and 30 steps of the simulation. So this is not enough for this front to meet. So this will be just the same as for a line, okay? So you can see that, okay, this black part is the classical walk, and this is the biquantum walk on the circle. So it looks very probably how it should look like if you compare it to this, because my initial condition was 0. So I started from I used kind of asymmetric, I made an asymmetric choice. And this is a result. I also studied click, but it is very uninteresting. And a lollipop, which was my main goal. I wanted to compare the classical and quantum performance. Of course, you cannot say much from this because there are only here 10 steps for n equal 3. So for n equal 3, I have 8 click, which consists of 8 nodes, and here 8 nodes. And my initial condition was 0, 0, 0 times 0, 0, 0, 0. 0, 0, 0, 0 times 0, 0, 0. Which meant that my initial position was just the node just by this highest valency node. And my initial direction was just along this loop. So this is the result. Here is the classical walk, and here is the quantum. I think this part is interesting because I wanted to look how fast it will take for my state, which start here, to go, for example, here. Of course, it depends on the choices I made here, but I think this part might indicate that in fact I achieved something in terms in comparison to the classical walk. Okay, and I think this is everything. I don't know how much time I used.
Perfect. It's 7:15.
Good.
Perfect timing.
So maybe as a quick summary, why quantum random walks might be interesting. First of all, we have some generic procedure for quantization of Markov chains, which can be used to achieve this quadratic generic speedup. I also gave you an example of a very specific problem of these glued trees, which was, I think, one of the first, if not the first example, of showing that there exists a problem which continuous quantum walk can solve, and there is no classical algorithm which can do it as good. And I wanted to show you that you can actually implement something and play with these walks, and I encourage you to try to implement something if you are interested, and maybe think about efficient implementations for other topologies. There are some papers about it for some Cayley graphs and things like that. So the interesting thing is what is the property of this graph really, which will enable us to have this efficient implementation. I think this is not, up to my knowledge, this is still not totally clear. So.
All right. Let's thank Oskar for the note. Do you have any questions to Oskar? I have one actually. So you are some experiments, you wrote some code, right? In lab. Is your code available somewhere? Is it open source or?
On my GitHub account, but it's not available, I think.
How is it available?
It's available for me,
Yeah.
yes.
Do you have any plans to just develop it further and maybe some people can join? Because I'm just thinking how difficult it may be for new people to start working on such topics, and I believe that if you have some plans for further research, further development, then perhaps it may be easier for people to just join or maybe at least ask you questions.
I think this is fairly easy to implement, but a bit tedious. I mean,
right.
well, I encourage you to do it as an exercise, so for your QSkit skills or something, and your understanding of this circuits, for example, and how they actually work in practice.
Okay.
Yeah, but maybe I will try to extend this to be able to do something in fact new. Maybe it's new. I mean, probably I don't know whether anybody implemented it. I have no idea. So, but it is not really, I don't have much data. And it is not like something.
So do you have,
it was just for my curiosity.
Okay. Do you have any specific plans for your further research on this topic? Because you mentioned that
yeah.
you started running experiments 2 years ago, right?
Yeah, I need to just rewrite my code for the new version of QSkit and run it using this fantastic option of just looking at the state vector. And then I will be able to generate and in fact compare these two algorithms. It is also possible that my implementation has a flaw, and in fact I cannot verify it.
All right, cool. Any more questions to Oskar?
Okay, so the conclusion for this problem is that basically it is difficult to get away from the clip. You stay in the clip,
Yeah.
it's very low probability to be in the tail.
Yeah, for the classical one, yes.
For the quantum one. No, sorry.
Black is the classical one.
Black is the classical, and blue is not really easy one finally. So, okay, so there is a much higher probability to get to the tail than classical. Okay.
I mean, it is not clear. I mean, this comparison, because sometimes quantum walk is worse, right? For example, it might be on a cycle. Sometimes it has period. Or things like that for some very specific numbers, which is something which happened to me, and I thought that it always has a period, but it turned out that this is just a specific choice of for small numbers, I chose to test. And
I cannot see my slides, but maybe I will just tell you briefly that the next meeting will be on 16th of December, and we'll also meet here in Codecool. And we are looking for next speakers. We have still slots for January, February, so if anyone of you is interested, then feel free to contact me. And yeah, you are welcome to give a talk. There was one question, or no? Okay, I found that there was a question. All right, so I thank you once again for coming, and thank Oskar for a great talk. And it's time for after party. So yeah, thank you once again, and let's go for pizza.